we're going to do this equivalence point calculation, number 2. You can see we've already got the answer here. It's supposed to be 8.73. So let's see if we can get to that answer. And on my work here, here it is, number 2. So now to the same solution, 20 mils of a 0.1 molar solution of acetic acid, we're now going to add 20 mils of a 0.1 molar solution of NaOH. We recognize my new volume is now going to be 40 milliliters, and something slightly different is going to happen in this calculation. So here I've got this big open blank sheet of paper. So we'll say number 2, and we're still going to start with this in the same way. This is a before and after table because we're adding a strong base to a weak acid, and we recognize those react to completion to make acetate and H2O, okay? And we remembered over here, because we already calculated how many moles that we're starting with, we're going to treat each of these calculations like separately, like as if this was 3 different experiments. The first experiment, we just added 10 milliliters, okay? And then in the second experiment, we started with a brand new fresh solution of 20 mil 0.1 molar acetic, and now we just add 20 mils. So because of that, because in this calculation number 2, we can assume we're just starting with a fresh solution, automatically I know that there's 0.002 moles, right? It's the same number right there. So instead of writing that calculation down twice, I'll just say I know that I'm starting with 0.02 moles here, okay? But now my hydroxide, so it was 20 milliliters of a 0.1 molar, and we'll go through and calculate that just to make sure. So we remember 20 milliliters is 0.02 liters, and that was 0.100 mole per liter. And so hopefully what you can see from there, that's going to give me 0.00200 moles. And now hopefully you recognize we're at the equivalence point because we have 2 millimoles of hydroxide and 2 millimoles of acetic acid. So those two things are equivalent. So it's at our equivalence point. And of course, 0 and 0. And we also recognize that all of both of these quantities are going to completely react, again, because we're at the equivalence point. And that means if 2 millimoles of our reagents are reacting, then 2 millimoles of our product is produced. Okay, and once again, I don't care about water, so we'll just cross it out. So now after I've got 0 of this, I've got 0 of this, and I've got 0.002 moles of the acetate. And so now what I need to do is convert that into molarity, and then I need to start a new calculation, okay? So we remembered that our new volume was 40 milliliters, right? So I'm going to divide that by 0.0400 liters, same as 40 milliliters, and that gives me 0.050 molar acetate. But now what we have going on here, we need to do a rice table, okay? And we could do this as a rice table, or if we were really good and recognized that we could just plug this straight into the KB expression, then we could do that as well. But because this is the first time we're seeing this, we'll just go ahead and start this as a new rice table. And so now that means I've got an RICE. My reaction is starting with the acetate, CH3COO minus, and that reaction is the KB reaction because we remember acetate is a conjugate base. So it's going to go on to produce hydroxide and the original acetic acid, okay? And when we look at our initial values, our initial value becomes this value right here. So we titrated away all this stuff. So we're going to say that's 0 and that's 0. But now this is the 0.05 molar, okay? And then we can see that because this is just our standard rice table, right? That's got to be plus x and minus x and 0.05 minus x, x, and x. And so now we need to figure out what k value we want. And we know that because this is the reaction that produces hydroxide, we want Kb. So I know that my Kb expression then is going to be related to x times x, all divided by 0.50. And I'll write the Kb value down here for acetate. It's 5.6 times 10 to the minus 10. And I got that Kb from the relationship Ka times Kb equals Kw, okay? So I knew the Ka of acetic acid was given right here. And I'm not showing that work right now, but I can rearrange and say Kb equals Kw divided by Ka. And I get that the Kb is 5.6 times 10 minus 10. And so because that's a crazy small Kb, my 5% rule is going to work out just fine. I'm going to skip a little bit of math here. I want you to prove that you can get this. But now when I solve this algebra, I get that x equals 5.3 times 10 to the negative 6. I remember that that corresponds to my POH. So now if I take 5.3 times 10 to the minus 6, and I take the log of that, so that's my POH, which is 5.27. And if I convert that into a pH, so over here I'm just going to say plus 14, I get the 8.72. And let's see how we did. Okay, so they're saying 8.73. Close enough for me. Okay, so probably our sig figs, got tied up somewhere around there. Okay, so let's summarize this again because these equivalence points calculations are lengthy. So we first need to do this before-after table. And we need to do this before-after table so that we can get the right concentration, right? Notice here that we had to consider the number of moles, and then we also had to consider the new volume. We then need to start a new rice table where now my final product ends up becoming my starting reactant, right? We then did a new rice table, and we can't use Henderson-Hasselbalch because this is no longer a buffer. And then that allows us to get the POH, which eventually gets the pH. So again, pretty lengthy on these equivalence points calculations because it involves both the before and after table and a rice table, and I want you to be able to do these style of calculations.